I could sail on the 7 seas with non-conservative practice problems. Okay, so this is practice problem 38 for non-conservative forces. And this means that we are going to have some non-conservative force kind of leaching energy from our problem for our conservation of energies here. In this problem, we have a 1.8 kilogram block, so we've got a nice mass here, and it's sliding on a rough horizontal surface. And while that surface is rough, that means there's going to be some friction. Non-conservative. The surface is at least horizontal, so we don't care about gravitational potential energy. It's not going to be a factor for us. What does happen is the block hits a spring with a speed of 2.0 meters per second, and it compresses it a distance of 11 centimeters before coming to rest. The coefficient of kinetic friction between the block and the surface is 0.56. What's the force constant of the spring? So let's just draw ourselves a little picture here. Here's a table. Here's a block. Block has a mass of 1.8 kilos, and it's initially moving to the right at 2 meters per second. When this block is moving at 2 meters per second, it hits a spring. And this spring is going to be compressed 11 centimeters, or 0.11 meters. There is some friction here on this ground, and that friction is going to act over the entirety of that 0.11 meters. After this, though, the block comes to rest, the spring is compressed, and we are looking for a force constant or spring constant, K. Take a second here, pause this video, and see if you can set up the equation for the conservation of energy with a non-conservative force in here, and then we'll go ahead and try to solve it. So, working through this, setting this up, hopefully you've got something there. If you don't, repause this and go do it. We know initially, because this block is moving, it has some kinetic energy. We can say this is a 1/2 mv squared, so 1/2 times 1.8 times 2 meters per second squared. There is no gravitational potential energy we care about because we're on a flat horizontal surface. And we haven't compressed the spring yet because it's not compressed and it's not stretched out. It's just at rest at an equilibrium position. There's no spring energy initially, but we know that some work is going to be done here due to the friction. So we'll just say plus W. We'll come back to that later. On our final side of things, we know that the block is going to wind up at rest. So there's no kinetic energy at the end. But we have compressed the spring. So we know there's going to be a 1/2 K x squared. And that spring compression we have is 0.11 meters squared. Now, this becomes a little bit tricky here because while we are looking for K, we have this unknown W that we've written in, which means we need to figure out what the work is so we can plug it into the problem and solve for K. So let's think about the work here. If this block is moving on the rough surface, we know the block is moving with some velocity to the right. It's going to have a displacement to the right of 0.11 meters because that's how much it compresses the spring. But friction is going to act to the left. So that's the force of friction, and we know the angle between them is 180 degrees. So if we actually use our work equation here, and we write everything out, so here's what we had initially, the 1/2, 1.8, 2 squared. Our work equation is going to be Fx cosine theta, where that F is the force, and that's the force of friction. Now recall that friction is Fun, which also equals mg, mu mg, for a flat horizontal surface. So we could write this as mu mg times delta x times the cosine of theta, which is 180. And this is going to equal our 1/2 kx squared, 0.11 squared. And if we put in some of the numbers we know here, we'll just rewrite this all again. I know it's a lot of writing, but this is how we do mathematics properly. So there's the 1/2 times the 1.8 times the 2 squared. We can put in some numbers here for this work. We know that the mu value here in this problem is 0.56. So we've got 0.56. We know the mass is 1.8. We know gravity is classic 9.8. We know the delta x is how far that block moved, which was the compression distance of the spring. So this is actually 0.11 meters. And then we know the cosine of 180 is actually equal to -1. And this is equal to 1/2 kx squared. So 1/2 k times 0.11 squared. So it looks here like there are a ton of numbers, especially during that work, because we had to say that work was fx cosine theta, and that force was due to friction, mu mg. We've got to put it all together. But in reality, this is a number that we're adding to this number. That's it. We are at the point now where the physics is all over. We are just number crunching at this point. So let's get our blue value for the kinetic energy. So 2 squared is 4 times 1.8 is 7.2 divided by 2 gives us a kinetic energy initially of 3.6. We're going to add that to this big quantity. So 0.56 times 1.8 times 9.8 times 0.11 times -1. We're going to get negative 1.09. And this is going to be equal to, I'm going to square the 0.11 and then combine it with the 1/2. So 0.11 squared is 0.0121 divided by 2 is 0.00605. So we'll call this 0.0061 K. So I've just kind of simplified and combined any numbers that I could together. And I guess in a way we're still doing that because these values need to go together. 3.6 minus 1.09 is going to equal 2.51. That's going to equal 0.0061 times K. And then we're almost finished. If we just divide by 0.0061, we find our K value as being approximately 411 newtons per meter. And if you didn't round to get the 0.0061, if you had 0.00605 or whatever, this would be a little bigger. It'd be like 415. But, you know, within rounding reasons, that's a great answer for us there. Okay? A lot of what we did in this problem, though, was just drawing that picture and walking through ideas of what energies do we have? Do we have initial kinetic energies? Is the spring initially compressed? It wasn't. Is there some work happening here? Of course there was. That was due to friction, and let's not forget that -1. The spring was compressed at the end, but the object was at rest, so there was no kinetic energy. That's all we're doing. We're just asking ourselves these questions as we work through this with our picture, and then once we asked ourselves the questions with this picture, we're able to put in all of these numbers. Even though it looks like a lot, they're just numbers. They just get multiplied and shoved together. And once we do that, we get something that looks very familiar within our world of algebra. So with that, this problem is finished. There are a ton more different types of problems you could do with non-conservative forces, but they all boil down to be the same thing. In our next upcoming videos, we're going to take a look at some collisions. Now, collisions are a little weird because we've already talked about them briefly when we did momentum, but we're going to revisit them for different types of collisions and what we can do with them in some weird cases moving forward. But until then, we are finished here. Adios, and take it easy.